Good day, ma'am. This is Shalika Janae Garilao, the Group 2 reporter, about the function. Function. The term function was first used by Leibniz in 1673 to denote the dependence of one quantity on another. In general, if a quantity y depends on quantity x in such way that each value of x determines exactly one value of y, then we say that y is a function of x. An equation will be a function if for any in the x in the domain of the equation will yield exactly one value of y. So class, always remember that if an equation will be a function, x in the domain of the equation will yield only exact one value of y. Given here the example, determine if each of the following are functions. So letter A and B. Letter A is y is equals to x squared plus 1. And letter B, y squared equals to x plus 1. The first one is a function. Given an x, there is only one way to square it and then add 1 to the resultant. So no matter what, the value of x you put into the equation, there is only one possible value of y. And letter B, the only difference between this equation, the first is that we move the exponent of the x and to the y. This small change is also that is required in this case to change the equation from a function to something that isn't a function. To see that isn't a function fairly simple. So choose a value of x is equals to 3, then plug into equation. So y squared is equals to 3 plus 1 equals to 4. So we could see that there is two possible value of y, and therefore we can say that it is not a function because a function says that x will yield only one possible value of y. Function notation. It is more than fancy way of writing the y in a function that will allow us to simplify notation in some of our work a little. Function notation gives us a nice compact way of representing function values. Let's take a look at the following function. Given here, y is equals to 2x squared minus 5x plus 3. Using function notation, we can write this as any of the following. Let's take the function above and let's get the value of the function at x equals to negative 3. Using function notation, we represent the value of the function at x equals to negative 3 as f quantity of negative 3. So the solution will look like f quantity of negative 3 equals to 2 times negative 3 squared minus 5 times negative 3 plus 3 and then simplify. Therefore, we can get that f quantity of negative 3 is equals to 36. All throughout, the calculus course will be finding roots of a function. A root of function is nothing more than a number for which the function is 0. In other words, finding the roots of a function, g quantity of x is equivalent to solving g quantity of x equals to 0. So now let's talk about function composition. The composition of f of x and g of x is quantity f composition of g of x equals to f quantity of g of x. Compositions are evaluated by plugging the second function listed into the first function listed. Note as well that order is important here. Interchanging the order will usually result in a different answer. Example, given f of x equals to 3x minus 2 and g of x equals to 1/3 x plus 2/3, find each of the following. F, composition of g of x, g, composition of f of x. Solution A will be f, composition of g of x is equals to f, quantity of g of x. And solution B, g, composition of f of x equals to g, quantity of f of x. And then substitute all the given values and you will get the final answer of a function.
Good morning everyone, I am Raylene A. Langsa and I will gonna tackle about the inverse function and the trigonometric function. So first, let us tackle the inverse function. An inverse function is defined as a function which can reverse into another function. Okay, now finding the inverse of a function. So given the function of f of x, we want to find the inverse function of f raised to negative 1 of x. So in finding the inverse of a function, we have 5 steps to be followed. First, replace every f of x with x. And second, replace every x with a y. And replace every x with an x. Then third, solve the equation from step 2 for y. And fourth, replace every y with f raised to negative 1 of x. And 5, verify your answer by checking that f of f raised to negative 1 times x is equals to x, and f raised to negative 1 of f times x is equal to x are both true. So here is our example in finding the inverse of a function. So we have the given of f of x equals to 3x minus 2. Find the f raised to negative 1 of x. So in finding this, we must follow the 5 steps in finding the inverse of a function. So first, let's get started with first replace f of x with y. Then we will have y equals 3x minus 2. The next, replace all x's with y and all y's with x. So we will have x equals 3y minus 2. Then now solve for y. So we will have x plus 2 equals 3y. Then we must have divide it by 3 to cancel the 3 and y. Then we will have the result of y. So x plus 2 over 3 equals 3y over 3. Then we will have the result of x over 3 plus 2 over 3 equals y. Then finally replace y with f raised to negative 1 of x. So we will have the answer of f raised to negative 1 of x equals x over 3 plus 2 over 3. Now, to check if our answer is true, we must use this formula. Quantity of f, o, f raised to negative 1 times x equals x. So, we have f, quantity of x over 3 plus 2 over 3, then 3, quantity of x over 3 plus 2 over 3, quantity minus 2. So, we have x plus 2 minus 2, then our answer is x, which is correct. So, trigonometric function. First, let's start with the 6 trigonometric function and how they relate to each other. So, given the cos quantity of x and sine quantity of x. So, later on, we will know how they relate to each other. Now, let's move on to the trigonometry function. So, we have 6 trigonometry function, which is first sine, cosine, tangent, cotangent, secant, and cosecant. So recall as well that all the trigonometric function can be defined in terms of a right triangle. So in a right triangle, we have an opposite, adjacent, and hypotenuse. So from this right triangle, we can get the following definition of the 6 trigonometric function. First, we have sine theta. We have opposite over hypotenuse. And we can also use its mnemonic name, which is SOH. And also, we have cos theta, adjacent over hypotenuse, or CAH or Ka. And tangent, we have opposite over hypotenuse, or SOHCAHTOA. And also, we have the cotangent, cot theta, we have adjacent over hypotenuse, and we have a mnemonic name of CAO, and also we have secant or sec theta, we have hypotenuse over adjacent, and we have a mnemonic name of SHA, and last the cosecant, SCS or SCS theta, and we have hypotenuse over opposite, and we have mnemonic of CHO. So we have here some basic angles in both degrees and region. So if we want to convert a degree or any angles to regions, we simply multiply the angles by and then divide it into 180. Then also we have the unit circle, because the unit circle is one of the most useful tools to come out of the trigonometry class. So, if we have the unit circle with just the first quadrant filled in, the way the unit circle works is to draw a line from the center of the circle outwards corresponding to a given angles. Then look at the coordinates of the points where the lines in the circle intersect. The first coordinate is the cosine of the angles and the second coordinate is the sine of that angles. We put some of the basic angles along with the coordinates of their intersect on the unit circle. So from the unit circle below, we can see that cosine quantity of pi over 6 is equal to square root of 3 over 2, and also the sine quantity of pi over 6 is equals to 1/2.
Good morning, everyone. I am Justin Villegas, best in my second year and reporter from Group 2, in which our topic is about function. So, my report for today is the continuation of report of Miss Shareka and Miss Rialin.
Remember how the signs of angles work. If you rotate it in a counterclockwise direction, the angle is positive. And if you rotate it in clockwise direction, the angle is negative. Recall as well that one complete revolution is equal to 2 pi, so the positive x-axis can correspond to either an angle of 0 or 2 pi, or 4 pi and 6 pi, and negative 2 pi and 4 pi, and etc. depending on the direction of the rotation. Likewise, the angle on the pick an angle completely at randomly can also be any of the following angles. We are here an example. Pi over 6 plus 2 pi is equal to 13 pi over 6. So the direction is start at pi 6 over 6, then rotate once around counterclockwise. So let's verify that pi over 6 plus 2 pi is equal to 13 pi over 6. Pi over 6 plus 2 pi is equal to pi over 6 plus 2 pi over 1, and equal to pi over 6 plus 6 times 2 pi over 6 times 1, pi over 6 plus 2 pi over 6, and pi plus 12 pi over 6. So let's add pi plus 12 pi. So it is equal 13 pi over 6. So we can see that pi over 6 plus 2 pi is equal to 13 pi over 6. Next, pi over 6 plus 4 pi is equal to 25 pi over 6. Verify that pi over 6 plus 4 pi is equal to 25 pi over 6. Pi over 6 plus 4 pi, then pi over 6 plus 4 pi over 1. Pi over 6 plus 6 times 4 pi over 6 times 1. Then pi over 6 plus 6 times 4 pi is equal to 24 pi over 6. Then pi over 6 plus 24 pi is equal to 25 pi over 6. So we can see that pi over 6 plus 4 pi is equal to 25 pi over 6. Thus, pi over 6 minus 4 pi is equal to 23 pi over 6. Verify. Pi over 6 minus 4 pi, then pi over 6 is minus 4 pi over 1. Then pi over 6 minus 6 times 4 pi over 6 times 1. Then pi over 6 is equal to 6 times 4 pi is equal to 24 pi over 6. Then pi minus 24 pi over 6. So pi minus 24 pi is equal to 23 pi over 6. So we can say that pi over 6 minus 4 pi is equal to 23 pi over 6. Evaluate the following. Cos 7 pi over 6 and cos negative 7 pi over 6. For this example, notice that 7 pi over 6 is equal to pi plus pi over 6. So this means we will rotate down pi over 6 from the negative x-axis to get to these angles. Also, negative 7 pi over 6 is equal to negative pi minus pi over 6. So this means we will rotate up pi over 6 from the negative x-axis to get to this angle. So, as with that last part, both of these angles will be mirror image of pi over 6 and the third and second quadrant respectively, and we can use this to determine the coordinates for both of these new angles. Both of these angles are shown on the following unit circles along with appropriate coordinates for the intersection points. Exponential function. Let's start with b greater than 0 and b is unequal to 1. An exponential function is then a function in the form f is to x is equal to b raised to x. X is equal to negative 4 raised to x. Let's do some evaluation. G of 2 is equal to negative 4 raised to 2 is equal to 16. So G of 1/2 is equal to negative 4 of raised to 1/2 is equal to the square root of negative 4 is equals to I. Example number 1. Sketch the graph of f of x is equal to 2 raised to x and g of x is equal to 1/2 raised to x. Solution. Let's first get the table of value for these two functions. X, f of x, and g of x. So, x, negative 2, and f of x is f, quantity of negative 2 is equal to 2 raised to negative 2 equal 1/4. So, g of x, g of negative 2 is equal to 1/2 raised to negative 2 equals 4. X, negative 1, f sub negative 1 is equal to 2 raised to 1 and equal to 1/2. G of x, g in negative 1 is equal to 1/2 raised to negative 1 is equal to 2. X, 0. F of 0 is equal to 2 raised to 0 and equal to 1. G of 0 is equal to 1/2 raised to 0 and equal to 1. X of 1. F of 1 is equal to 2 and g of 1 is equal to 1/2. 2. F of 2 is equal to 4 and g of 2 is equal to 1/4. So this is the graph of the example number 1. Properties of f of x is equal to b raised to x. So number 1, f of 0 is equal to 1. The function will always take the value of the 1 and x is equal to 0. Number 2, f of x is equal to unequal to 0. An exponential function will never be 0. Number 3, f of x is greater than 0. An exponential function is always positive. Number 4, the previous two properties can be summarized by saying that the range of the exponential function is 0. Number 5, the domain of an exponential function is negative infinity and infinity. In other words, you can plug every x into an exponential function. Number 6, if 0 is less than b and less than 1, then f of x is to 0 as x is to infinity. Then b, f of x is to infinity as x is equal to negative infinity. Number 7, if b is greater than 1, then a, f of x is infinity as x is infinity. Then b, f of x is 0 as x is negative infinity. Definition. The natural exponential function is f of x is equal to e raised to x, where e is equal to 2.7182, 81, 82, 84, 59, and 05. Example number 2. Sketch of each and of t is equal to 1 minus 5 e raised to 1 and 1/2. Solution. Let's first get a table of value for this function. Our f is negative 2, negative 1, 0, 2, and 3. So our h and of t is negative 35.9453 and negative 21.4084, then negative 12.5914 and negative 7.2436, then negative 4, negative 2.037. So let's graph it. The value of our 2 is negative 4. So our line start at below of negative 5 because the value of our 2 is negative 4. Then the value of our 1 is negative 7.2436. So in 1, the line pass before negative 10. For center or our 0, the value is negative 12.5914. So the line pass away and below of negative 10. And our negative 1 is negative 21.4084. So the line pass after negative 20. Then last, our negative 2, the value is negative 35.9453. So the line pass below in negative 35. Logarithm functions. Logarithm are one of the functions that students fear the most. The main reasons for this seems to be that the simply have never really had to work with them. Once they start working with them, students come to realize that they aren't as bad as they first thought. Well, start with b greater than 0 and b is unequal to 1, just as we did in the last section. Then we have y is equal to log x is equivalent to x equals b raised to y. The first is called logarithm form and the second is called the exponential form. Remembering this equivalence is the key to evaluating logarithms. The number b is called the base. Without a calculator, give the exact value of each of the following logarithms. A. Log 16. First, let's convert to exponential form. Log of 2. 16 is equal what? And equivalent to 2 raised to 4 is equal to 16. So, we're really asking 2 raised to what gives 16. Since 2 raised to 4 is 16, we get log sub 2 16 equals 4 because 2 raised to 4 is equal to 16. We'll let do the remaining parts and quiet these details, but they will all work in this way. B. Log sub 4 16. Log sub 4 16 equals to 2 because 4 squared is 16. Note the difference the first and second logarithm. The base is important. It can completely change the answer.
There are a couple of special logarithms that are arise in many places, and these are the ln x equals to log base e x, and this is called the natural logarithm. And the next is log x equals to log base 10x. This log is called the common logarithm. And in the natural logarithm, the base e is the same number as n the natural exponential logarithm that we saw in the last section. Here is a sketch of both of these logarithms. So from this graph, we can get a couple of very nice properties about the natural logarithm that we will use many times in this and later calculus courses. Let's take a look at a couple or more logarithm evaluations, some of which deal with the natural or common logarithm and some of which don't. So, sample. So, without calculator, give the exact value of each of the following logarithms. So, letter A is ln cube root of e. So, and letter B, log of 1000. Letter C, log base 16 times 16. Letter D, log base 23 base 1. So letter E, log base 2, 7th root of 32. So we we compute this in this solution. So this work exactly the same as previous example. So we won't put into many details. So in letter A, ln cube root of E equals to 1 third because E exponent of 1 over 3 is equals to cube root of E. Letter B, log of 1000 equals to 3 because 10 exponent of 3 is equals to 1000. And letter C, log base 16, 16 equals to 1 because 16 exponent of 1 is equal to 16. So letter D, log base 23 times 1 equals to 0 because 23 exponent of 0 equals to 1. And letter E, log base 2, 7th root of 32 is equals to 5 over 7 because 7th root of 32 is equal to 32 exponent of 1 over 7. And it is equal to 2 exponent of 5 and raised to the power of 1 over 7 and equal to 2 exponent of 5 over 7. This last set of examples leads us to some of the basic properties of logarithms. And the properties are number one, the domain of the logarithm function is 0, comma infinite. In other words, we can only plug positive numbers into a logarithm. We can plug in 0 or a negative number. And number 2, log base b times b is equals to 1. And log base b times 1 equals to 0. And number 4, log base b times b exponent of x equals to x. Then number 5, b exponent of log base b times x is equal to 1. The last two properties will especially useful in the next section. So notice as well that these last two properties tell us that f of x is equal to b exponent of x and g of x is equal to log base b times x are inverses of each other. So more properties and we are going to number 6. So log base b times xy equals to log base b times x plus log base b times y. And number 7, log base b times x over y equals to log base b times x minus log base b times y. And number 8 is log base b times x exponent of r is equal to r log base b times x. So note that there is no equivalent property to the first two for sums and differences. In other words, log base b times x plus y is not equal to log base b x plus log base b y. And log base b times x minus y is not equal to log base b x minus log base b y. So ln x exponent of 3, y exponent of 4, z exponent of 5. So property 6 above can be extended to products of more than two functions. Once we've used property 6 we can then use property 8. So ln x exponent of 3 times y exponent of 4 z exponent of 5 is equal to ln x exponent of 3 plus ln y exponent of 4 plus ln z exponent of 5 and it is equal to 3 ln x plus 4 ln y plus 5 ln z. So, and the next is log base 3 times 9x exponent of 4 over square root of y. When using property 7 above, make sure that the logarithm that you subtract is the one that contains the denominator as its argument. Also, note that we'll be converting the root to fractional exponents in the first step. So log base 3 times 9x exponent of 4 over the square root of y is equal to log base 3 times 9x exponent of 4 minus log base 3 y exponent of 1 half is equal to log base 3 times 9 plus log base 3 times x exponent of 4 minus log base 3 times y exponent of 1 and 1 half. And it is equal to 2 plus 4 log base 3 x minus 1 half log base 3 y. And the log times x squared plus y squared over x minus y cubed. So the point to this problem is mostly the correct use of the property 8 above. So log x squared plus y squared over x minus y cubed is equal to log x squared plus y squared minus log x minus y cubed is equal to log x squared plus y squared minus log 3x minus y. You can use the property 8 on the second term because the whole term was raised to the 3. But in the first logarithm, only the individual terms were squared and not the term as a whole. So the 2's must stay where they are. The last topic that we need to look at in this section is the change of base formula for logarithm. The change of base formula is log base b times x is equal to log base a times x over log base a times b. So this is the most general change of base formula and will convert from base b to base a. However, the usual reason for using the change of base formula is to compute the value of logarithm that is in a base that you can easily deal with. Using the change of base formula means that you can write the logarithm in terms of a logarithm, that you can deal with the two most common chains of base formulas are. So these are log base b times x is equal to ln times x over ln b, and log base b times x is equal to log x over log b. So in the first part of this section, we computed the value of a few logarithms. But we could do this without the change of base formula because all the arguments could be written in terms of the base to a power. For instance, log base 7 times 49 is equal to 2 because 7 exponent of 2 is equal to 49. However, this only works because 49 can be written as a power of 7. We would need the change of base formula to compute log base 7 times 50. So, log base 7 times 50 equals to ln 50 over ln 70. So, ln 50 is equal to 3.9120 to 300,543 over the value of ln 7 equals to 1.94591014,906. So, is equal to 2.0103821378, or log base 7 times 50 equals to log 50 over log 7. So the value of log 50 is 1.6989700,434 over the value of log 7 is equal to 0.845098040014. So it is equal to 2.0103821378. 7, 8. So, in this section, we saw how logarithms work and took a look at some of the properties of logarithms. We will run into logarithms on occasion, so make sure that you can deal with the same when we do run into them. Thank you.